began with simple cells. Cells contain DNA, the genetic instructions for all life, influencing everything from the color. This region contains enough gas and dust to produce perhaps 1 million stars. And not just stars, but planets too. The turbulent flow of gas and the inexorable pull of gravity create pockets of tremendous activity. Our sun, Earth, and sibling planets formed in such a place. A slowly active, watery world before life had turned the oceans blue. All life on Earth depends on liquid water. If we're looking for places where life might have taken hold, it makes sense to look in the vast primordial ocean. Let's dive into complex organic molecules. Short chains of carbon, oxygen, hydrogen, and nitrogen atoms link steps toward life. Continents are still taking shape, but volcanic islands have emerged from the ocean surface. Rainwater, heated by sunshine, collects in hot puddles. This tiny pool is shrinking and drying in the sun, concentrating its contents, but gathering clouds promise a wetter future. A microscopic view reveals oily layers of molecules called lipids, with nucleotides mixed in. Nucleotides link together to spell out the instructions stored in DNA. Moistened by rain, our hot puddle grows wetter, and the lipid layers balloon into tiny water-filled bubbles that may well have been the precursors of modern cells. The lipid layers remain stable in water, protecting what's inside. The language of DNA won't evolve for a very long time. But perhaps those early nucleotides linked together to spell a few simple words. Early instructions that would evolve into our modern genetic code. It took perhaps 1 billion years, but life eventually harnessed the power of sunlight through photosynthesis. This changed our world. Microorganisms called cyanobacteria developed a type of photosynthesis that makes oxygen. The tiny microbes thrived, filling Earth's oceans and atmosphere with oxygen. Similar communities of bacteria exist today, building microbial reefs in shallow, salty waters. The ancestors of today's cyanobacteria released enough oxygen to remove the greenhouse gases that kept our planet warm. Temperatures dropped, and our planet probably plunged into its first global ice age. Microscopic life transformed the entire planet. Nearly 2 billion years later, with microbial life flourishing in the oceans, our world experienced another long, deep freeze. When Earth thawed out, an explosion of life took place. Single-celled creatures started sticking together, leading to early multicellular life. Initially, similar cells organized into life forms that may have resembled modern sponges. Individual cells eventually took on specialized functions. while working together as a single organism. Life evolved into a variety of configurations. Primitive algae gave rise to plants, which eventually colonized land. The continents turned green with vegetation. A wet rainforest, like today's Amazon Delta, probably looks a lot like the vast swamp that existed on Earth back then. A multitude of species depending on one another for survival. By the time of the dinosaurs, Earth had dried out. Land had linked together to form a vast supercontinent with hot summers and freezing winters. The first flowers bloomed, tiny ancestors of some of the most diverse and successful plant families. The supercontinent eventually split into land masses a billion years in the past, an active, watery world before life had turned the oceans blue. All life on Earth depends on liquid water. If we're looking for places where life might have taken hold, it makes sense to look in the vast primordial ocean. Let's dive in. Unique and complex structures assembled from a multitude of cells. These elaborate life forms emerged more than 750 million years ago. In the Canadian Rockies, an outcrop known as the Burgess Shale records the remains of complex creatures that thrived during the explosion of life that occurred after Earth's last great thaw. Distinctive trilobites, soft-bodied worms, and puzzling crustaceans